All right, so welcome everybody. Here are our goals tonight. We're going to continue in section 4.4 with the definition of divides. We're going to look at some proofs and a counterexample. And then we're going to look at standard factored form, standard factorization of perfect squares and perfect cubes. Of course, you know what a perfect square is because you just submitted a homework where you had to use the definition of a perfect square. But we're going to look a little more in depth into what it means for a number to be a perfect square and a perfect cube. You should also know that I'm going to drop a video this weekend, just a real short video that's going to show you how to work a particular kind of problem that's going to appear on special homework number 6, which will go up tonight and be due next Wednesday night. Okay. So again, there was a quiz earlier today. What you see in black was what I wrote, and then students filled in the blanks on their own paper. So you could, it was just a test to make sure that people actually knew the definitions by heart. At this stage of the game, you kind of need to know those definitions by heart. Does anybody have any questions before we get started tonight? I assume everybody's looked at your test and seen your the comments and things. Solution to test 1 will get posted probably over the weekend so that you have that for your reference. That material is, of course, fair game for the final exam. All right, so last time on day 11, we proved this statement. For all A, B, and C in Z, so for all integers A, B, and C, if A divides B and A divides C, then A divides B plus C. So we proved that and we practiced with the definition of divides. And tonight we're going to, like I said, continue with proofs using this definition. And of course, notes will be posted. So what I'd like to do with you right now is just review the definition of divides. Remember, we say x divides y. We're talking about integers, of course. And x is not 0 because we've never tried to divide by 0. X divides y if y is equal to x times k, where k is an integer. So when I read this phrase, x divides y, I realize it's a statement, and you need to realize this is a statement. It is not a number. When you draw this vertical line, it needs to be perfectly vertical. Okay. And so it's not confused with the number x divided by y. So that's what confuses students, I think, is this notation. X divides y, when you think about it, you could say to yourself, x divides into y. In other words, y is the bigger one. They might be equal, but for sure, x cannot be larger than y and divide into y. All right. So we're going to keep this handy all evening because this definition, again, is the definition that we're going to be practicing all evening. So we're going to move on and prove another proof involving the definition of divides tonight, and slightly different. So here we go. Let's get started with our first example. Oh, I'm going to give you a couple of do-laters just so that you can get a little more practice with this definition of divides. Prove them, prove these two statements. Okay, the first statement is for all A, B, and C in Z, if A divides B and A divides B plus C, then A divides C. This looks a lot like the statement that we proved on day 11, but it's a little bit of a twist on that. So see if you can prove that. And here's one more to do later. For all A, B, and C in Z, if A divides B minus C and A divides C, then A divides B. So these will give you practice, and these look a lot like the proof that we did prove last time, Monday night on day 11. Let's do something a little different now. Example 1, we're going to have another proof involving divides. Yeah, we're deep into it now, folks. We are deep into our proof writing portion of the course. Example 1. Proof. For all A, B, and C in Z, so these are integers, A, B, and C, if A divides B and B divides C, then in fact A divides C. So it's already written as an if-then. It's a universal statement, of course. So we can see the hypothesis that A divides B and B divides C. We're using the direct proof method, and we know that when we're proving an if P then Q using the direct proof method, we assume the hypothesis P, and then we wish to prove the conclusion, what we would call Q, if we labeled those. Okay. So I'm going to keep this definition of divides right up here where we can see it. Here we go. Let's write the proof. I'll use blue. So we assume that A, B, and C are integers. You could say let, that's a word that can be used instead of assume or suppose. Let A, B, and C be integers. And we're going to assume, of course, the hypothesis that A divides B and B divides C. Okay. Well, what do we wish to show, folks? Well, it's right in front of us. We wish to show the conclusion. We wish to show that A divides C. Okay? And now we break out this definition of divides and we use it because we have a hypothesis. We know that A divides B and B divides C. Let's write those equations and the other information that we get from knowing that. By the definition of divides, we always let our reader know what definition we're using. It's just considered polite so that your reader can keep up with what we're doing. All right, first of all, A divides B. So A is playing the role of X and B is playing the role of Y. So instead of Y here, we're going to have B equals A times K. So here we go, B equals A times K, where K is an integer. And of course, we also know that B divides C. Okay, so now when we use the definition of divides, B is the X and C is the Y. So B is dividing into C. So our equation is that C equals B times, some integer, we need a letter. I'll just keep going with KJ, where J is in Z. So let's just take stock. Let's just take a look at all of this great information that we have just from the hypothesis. We have an equation that B equals A times K. We've got information about K. It's an integer. We've got an equation that C equals B times J and information, of course, about J. Now, it's especially helpful with the definition of divides to unpack the wish. Like, what does it mean to say that A divides C? What is the work that we would need to do to prove that A divides into C? Let's write that down. What we wish to show is that C, that's the Y now, is equal to A, which is the X, times, I'll say M, we need a new letter, where M is in Z. So that's our wish. This whole idea of writing down a wish, like what do we wish to do, and then expounding on that wish, originated from proofs by mathematical induction that I was teaching, but also this idea of expounding on the wish actually arose specifically because of the definition of divides. Because the definition of divides is just a little bit tricky. You see, if we don't really unpack what A divides C means, we may not be aware that what we need to be looking at is C. Because if we just read A divides C, we might be thinking that we need to do something with A. Well, A is involved, but what we really need to be looking at is C. We're going to show it is a multiple of A. So let's take a look at C and let's see what we can do with it. No pun intended. So we want to get C looking like A times an integer. All right. So what do we have right here in our proof money that we can use to substitute in for C?
C is equal to A times K times J.
Wow, you're a step ahead of me. Do you mind if I do that in 2 steps? Good job. Well, first, C is equal to B times J. But then we really need an A, right? And there's not an A here. That's when we use the substitution that B is equal to AK. So that's AK times J. And then we can use the associativity of multiplication and regroup this so that it's A times the product KJ. So yeah, you got to that real quick. Nice job. But I'm going to show the steps here. And folks, the M that we're looking for, the integer M, it's right here. It's going to be K times J. That's going to be our M. So we started with C, and we turned it into an expression that has a factor of A and the factor KJ, which is going to be our M. So we just burned this proof money and this proof money. We've just used both of those. Okay. We used them here, and we used it again here. We haven't used this proof money yet. That's what we're going to use to prove that M is an integer. We use the fact that K and J are integers to prove that M is an integer. And of course, we'll use the fact that products of integers are integers. So let's write that up. Since K is in Z, so we're using this, and J is in Z, so now we've just used the last bit of our proof money. And products of integers are integers. That's one way to say it. We have M equals K times J is an integer, or you could say is an element of Z if you prefer. I try to write the proofs, different ways. You can find your own style, or whatever you're comfortable with. So let's just wrap it up. Let's just tell our reader what we just did for him. So C equals A times M, where M is in Z, it's an integer, which means A divides C by the definition of divides. So it's simple substitution. If we get our equations right, we're all set. And getting our equations right is just a matter of practicing with that definition of divides until you feel comfortable with it. Questions? All right, I'm going to give you a couple of do later problems, and then we are going to work another proof because one of these do later problems might scare you a little bit. I don't want to scare you, so just want to reassure you that you're going to get some instruction. Leave this up here for a minute. So here's a couple of do later problems. And doing do later problems, if you sit after class for 15 or 20 minutes and just, read through the notes and sort of organize them instead of, just getting up and walking away, it can give you a good chance for this stuff to soak in. It can be a really good habit to rewrite your notes. So 3, because we already have 2 other do laters. Prove. And this will be for all A, B, and C and Z, as usual, when we have these divides problems. If A divides B and B divides C, then A squared divides C squared. You should be able to prove that. Here's another one. Prove for all A, B, and C and Z. If A, oh, and D, I only said C. Yeah, the notes are wrong that are posted. We need to add a D in here because we've got 4 variables. I forgot the D. If A divides B and C divides D, then AC divides 3BD. So there's nothing hard about these. It just takes a little pin pushing, and the practice should be helpful for you. All right, let's do another proof. Let's do a proof with some exponents because I've played into this exponents idea here. Let's go for that. If A divides B and A divides C, then A cubed divides B squared C. So we're going to prove that. All right. So let me put the definition of divides up here where we can see it. Here we go. Start our proof. We're going to let A, B, and C be in Z. It's good to tell your reader what those variables represent. And we're going to assume A divides B and A divides C. So that's our complete hypothesis there. Right? We take the hypothesis. Well, what do we wish to show? Well, we wish to show A cubed divides B squared C. It's very methodical. Each step is easy in its own right. You just have to go through these steps to carefully craft our argument. So we have our hypothesis, we know what we want to do, and now we hear the voice, the Halloween voice that says use the definition and it's divides, of course. By the definition of divides, we have, okay. Take a minute and see if you can write the two equations that you get, plus the additional information about your new variables from the hypothesis that A divides B and A divides C. And I'll be using the usual suspects. I'll be using K and J, in case you wondered. I'm going to just check on the gallery. Hoping everybody's got pencil and paper and is working, or an iPad or something. Okay, so A divides B. So B is equal to A times K, where K is in Z, and A divides C, so C is equal to A times J, where J is in Z. Now unpack your wish. What do we actually wish to show? Let's see. The X is A cubed and the Y is B squared C. So we want B squared C to equal A cubed times, I'll say M, where M is in Z. Everybody keeping up? All right. So the nice thing again about unpacking the wish is it shows us, oh, we got to look at B squared C, right? We're not going to be looking at A cubed. We're going to be looking at B squared C. So let's take a look at B squared C and see what we can do with that. Well, B is A times K, so we can plug in A K for B, and that's getting squared. We'll need that. Times C. And if you think ahead, AK quantity squared is A squared K squared, right? Because of rules of exponents, we can distribute this 2 across the two factors, right? In general, you know, the rule is that if you've got a product, you know, x, y, raised to some exponent n, you can distribute that exponent across the factors. That's the general rule for exponents. So we can see ahead that we're going to get an A squared out of this, but we are going to need an A cubed. So we're one short. We're one factor of A short. And that should remind us, oh, we can still plug in for C because we have an expression for C, namely A times J. And so now we've got enough A's. We've used both of these, okay? So it's not like we can do any more substitution here. So what do we have? We have A squared, K squared, AJ. And if we rearrange the terms, and you don't have to show all these steps. If your algebra is strong, that's great. I'm just doing this to just help people that may be a little rusty with their laws of exponents. But here, if we put these two bases that are A, so A squared and A, actually this is A to the 1, even though we don't usually write the 1, it is A raised to the 1. And just remember that if we have, here's another rule, X to the M times x to the n, what do we do with the exponents? What's the rule? Anybody remember the rule?
Add them.
Yep, we'll add the m plus n. Good, thank you. And so, like I said, we don't usually write the 1, but there is a 1 there. So when we keep going, we've got a cubed. And that makes sense, right? It's 2 copies of A times another copy of A. We've got 3 copies of A being multiplied together times this quantity k squared j. And of course, great. That's the first part of what we needed. We got b squared c looking like a cubed times something. That's our m. And we just have to argue that m is an integer. Once we've argued that m is an integer, this proof is done. So let's argue that m is an integer using, of course, the fact that k and j are integers. So since k is in z and j is in z, m equals the quantity k squared j is in z because z is closed under multiplication. See, this is the other way you can say it. Instead of saying products of integers are integers, you can invoke closure. Z is closed under multiplication. And so we've gotten part 2 of the definition of divides done. We've just argued that m, which is our k squared j, is an integer. So now we can just wrap it up. So b squared c equals a cubed times m, where m is in z, which means a cubed divides b squared c by definition of divides. And that's what we wanted to show. Any questions? So we have seen now a total of 3 proofs involving the definition of divides. And between these 3 proofs, you should have enough, of information so that you'll be able to work special homework problems and understand WebAssign problems. But there's another game. We can disprove statements. We can disprove false statements involving divides. Why don't we look at one of those? Disproving false statements. So example 3, consider this false statement. For all A, B, and C in Z, if A divides BC, then A divides B or A divides C. All right, so this is a false statement. And let's just take a look at it so we can kind of get a handle on what are we going to have to do here, right? Well, what's the game going to be? Well, it's a universal statement. It's a for all statement. And of course, that makes sense because it's an if-then, and we know every if-then statement is a for all statement. So it's an if P then Q, and our Q is a compound Q here. So the instructions are to disprove the statement. By giving a counterexample. Of course, that's nice to be told that that's what you have to do. But at this stage of the game, you should know if you're disproving a universal statement, you will be giving a counterexample. So we're going to be proving the negation. So let's look at the negation first. Let's look at the negation so that we know what it is we're actually going to be proving. So here's the negation. Well, the negation is going to be an existence statement. There exist A, B, and C in Z such that, all right, so the negation of if P then Q is P and not Q. So of course, P is A divides BC and the negation of Q. So we're going to learn some new notation now. The way that we negate A divides B is we say A does not divide B, and guess what? The notation is just what you think it should be. You just put a slash through divides. This means A does not divide B. The or, because we're negating Q, flips to an and by De Morgan's laws, of course. And then we negate A divides C. So we write A does not divide C. So this is our new notation, does not divide. It would be a good idea for us to take a minute and think about what that actually means, okay? What does it mean to say X does not divide Y? X does not divide Y means that Y divided by X, that's a number, is not an integer. That's what X does not divide Y means. Okay, so it's good for us to know what we're dealing with here. So we're going to do some scrap work because we're going to try to prove this negation, and it's an existence statement. And we need to cook up some examples, or at least an example of an A and a B and a C that are integers. And A is going to have to divide BC, but A cannot divide B and A cannot divide C. So listen, it's the usual kind of suggestion when you're looking for a counterexample is keep it simple. Don't go off the deep end with really big numbers, right? So I just want to just show you a particular attempt to show you what it, oops, sorry about that. Let me get my camera back on. To show you what it looks like for a problem that's, this complicated here, okay? So let's try A equals 2, B equals 3, and C equals 4. The reason that I'm trying 2 is for A is it's just the simplest number I can think of. I know 1's not going to work because 1's going to divide B and 1's going to divide into C. So I know I'm not going to use A equals 1. So what about 2? Okay, let's try 2. And I know we want A to divide B times C. So there's going to have to be a 2 as a factor in B times C, and there's a 2 in 4. So B times C is going to be 12. That's going to work out. So let's see how this works out. We have to check 3 things. We're going to check, does A divide BC? Right? Because A has to divide B times C. Let me get this G out of my way. I think that G is kind of in our way here. A has to divide B times C. Well, let's see. Does 2 divide 3 times 4, which is 12? Yep, it does, right? Because 12 is equal to 2 times 6. You know, 6 is our K. So far, so good. A divides B times C. But now we got to check and make sure A does not divide B, and we're going to have to check that A does not divide C. So you can see where this is going. Let's check. Is it true that A does not divide B? In other words, is it true that 2 does not divide 3? Well, let's just remember here we've got this information. 2 does not divide 3 means 3 over 2 is not an integer. Yeah, 3 over 2 is not an integer, right? It's not an integer. So good. Check. So far, so good. Last thing we got to check. We got to check that A does not divide C. Here we go. A does not divide C. Is that working? Is it true that 2 does not divide 4? Oh, well, 4 divided by 2 is 2, which is an integer. So this did not work because we need 2 to not divide C as well as not divide B. You see what's going on here? All right. Now, this is the hint. This is the thing to understand. If we use a prime number for A, we're never going to be able to get it to work out as a counterexample. Let's think about why a prime will never work out for A. If A is prime, like 2 or 3 or 5, and we know it divides B times C, there's no way we can split a prime up and give part of it to B and part of it to C. See what I mean? Like 2, you can't split 2 up and give part of it to B and part of it to C because 2 is prime. So 2 will always have to either divide B or C. Does that make sense? The whole of 2 has to fit into one of these numbers as a factor. So the deal is we have to use an A that's not prime because we're going to want to give part of A to B and some other factor of A to C so that all of A does not divide into B or C. So when we start looking, we're going to keep trying till we find a counterexample. We cannot use a prime for A. All right, so now I'm thinking to myself, okay, I can't use a prime for A. I want to keep these numbers as small as possible. The smallest non-prime number that would make sense to use would be to try A equals 4. That's not prime. It's 2 times 2. And maybe we could give one of the 2's as a factor in B and one of the other 2 that's in 4 as a factor in C. And then 4 will divide B times C, but it won't be able to divide into B or into C because we don't want to give B and C both of those factors of 2 that fit into A. So, let's try this. B could equal 6, for example, and then we could just let C equal 2. Let's see if that works. Let's go through our check. We've got 3 things we have to check here. We got to check that A does divide B times C. We're going to have to check that A does not divide B, and we're going to have to check that A does not divide C. So first, let's check that A divides B times C. Is that true? Well, does 4 divide 6 times 2, which is 12? Sure. 12 is 4 times 3, right? 3 is the K. So 4 definitely divides into 12. So far, so good. Now we have to check that A does not divide B. We need to check that 4 does not divide 6. So we check our definition, does not divide, and 4 does not divide 6 means 6 over 4 is not an integer. 6 over 4, well, that's 3/2, yeah, and that's not an integer. So 4 doesn't divide 6. See how this is going? And then finally, we have to check that 4 does not divide 2, and it won't. A does not divide C because 4 does not divide 2. Why? Because 2 over 4 is not an integer. So we have found our counterexample that satisfies the negation of the original statement that we're disproving. So all we have to do is write it up. Writing it up is basically presenting these numbers and verifying, just writing this stuff that we've already written, but putting it in the proof itself. Formalizing it, making it look nice. All right, I'm going to fold this so we can see our good, so we can see what we've got here. All right, so we're going to write this up. So it's example 3, counterexample. Oops, I want to use blue. Right. So consider, just, that's a good way as any to tell your reader, hey, I've thought about this. Consider A equals 4, B equals 6, and C equals 2. And then you just go through. Of course, we have to verify that these are integers. We always have to verify that our example objects live in the correct domain. But that's easy. You can just say it. Everybody's going to believe you if you say, hey, these are integers. Clearly, these are integers. It's not that often that we can just say, hey, obviously, thus and such, but we can do that here. And now we're going to just write up all this other stuff. Notice, just because I want to start a sentence with a capital letter, A divides BC because 4 divides 12, since 12 equals 4 times 3. A does not divide B because 4 does not divide 6, since 6 over 4 is not an integer. See the difference between a slanted line and the vertical line? See, this is a number, this is a statement. See, this is a statement, but that's a number. That's what tends to get students a little mixed up. A does not divide C. Why? Because 4 does not divide 2. Since 2 over 4 is not an integer. And that's it. Basically, we just write up our scrap work. And we have proven the negation. Right, that's what we had to do, is prove the negation. That's it. Questions? Answers? Okay. All right. So let's shift gears a little bit. I think we've done enough with divides for one evening, right? We're We're going to still talk about the idea of factors and prime factors and things like that, but let's just shift gears. We're still in section 4.4, but we're going to talk about a theorem called the unique factorization theorem. So we're going to switch gears and talk about unique factorization and standard factored form. This is kind of a fun game. I've got some tricks up my sleeve I want to teach you. Standard factored form. So here's the theorem, the unique factorization theorem. Remember when we learned the definition of prime and composite, that those two definitions only applied to integers that were at least as large as 2? Well, the unique factorization theorem only applies to integers that are at least as large as 2, and you'll see why. Given any integer n greater than or equal to 2, there is a unique factorization of n into a product of powers of primes. In other words, there is a unique way to write n as follows. Here we go. All right, so fasten your seatbelts because we are getting ready to see some subscripts, some indexing subscripts, and there's going to be a good reason for them. So n is equal to p sub 1, so that's supposed to be the first prime factor of n, raised to the e sub 1. So maybe some number of copies of that prime fit into n, times p sub 2. That'd be the next biggest prime that is a factor of n, raised to e sub 2. That's the number of copies of that prime that fit into n, times dot, 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 keep going, times, say, p sub k, that'd be the biggest prime factor of n, raised to the e sub k. Now listen, we've learned a lot about definitions over the last week or so. One of the things that we learned is that definitions have more than one part. And a lot of times those extra parts of the definition are the parts that tell us that, hey, k is an integer, right? Or whatever the variable is, what does it represent? So look what just happened here. We have introduced a bunch of variables, but n was the original number we were given. We didn't introduce that per se. But look, we introduced P1 and P2 and PK. Hey, we introduced K, which represents the number of different prime factors of n. And we introduced E1 and E2 up to EK. We got to tell the reader what all that stuff means. So here we go. Let's do this work. Where, okay, first, each piece of I is prime. 1 less than or equal to I less than or equal to K. That means for each of these piece of I's, piece of 1, piece of 2, up to piece of K, they're all representing primes. By the way, when K is used as an indexing number in the context of our course, it's understood it's representing an integer, okay? A positive integer. It's not going to be smaller than 1. We never count down with our indexing numbers in the games that we play in this class. you start with indexing number 1, then the next indexing number would be 2, and then we understand we keep going up. We increment by 1, by 1, by 1 until we get to the top indexing number. So we understand this is an integer. Now, one of the things that we want to say somehow, mathematically, is that these primes are in order by size. We want to somehow express the idea that p sub 1 is less than p sub 2, and p sub 2 would be smaller than p sub 3, and keep going up to the point where we understand p sub k is the biggest of all the prime factors that are prime factors of n. How do we say that mathematically? Well, we use the indexing numbers to help us, because the indexing numbers are what give order to these factors. So we say p sub I is less than p sub j whenever I is less than j. I want this to be a whenever, out of wherever. Whenever I is less than j. And this is for 1 is less than or equal to I, is less than j, is less than or equal to k. So, I mean, let's just make sure you understand what this is saying. This is saying prime sub I is smaller than prime sub j when the indexing number I is less than j. So that means p sub 1 is less than p sub 2. P sub 2 is less than p sub 3. See what I mean? This is the way that we say that these are in ascending order by size. And finally, we need to treat these exponents. Now, does anybody in here remember what happens when you raise a number to the 0, the exponent 0?
It's
What is
1.
It's 1, right. So what we don't want is a bunch of superfluous prime factors raised to the 0. Because then, where would we stop? We could just keep adding a bunch of prime factors and raise them all to 0, and they might not have anything to do with n at all. So we don't allow the 0 as an exponent. We want all of these exponents to be, at least 1. So e sub I is a positive integer. It's in the z plus. For 1 less than or equal to I is less than or equal to k. So it took all of this to explain this. And we're going to call this equation for n equation star, okay? So in fact, equation star is called the standard factored form of n. This is called standard factored form. SFF of n. So the unique factorization theorem gives us a standard factored form of n. So it looks a lot worse than it is. Okay, let's play the game. Let's do this. Let's find the standard factored form of a number n, an integer n, so that you can start to feel more comfortable with all of these indexing numbers and everything. So we're going to play standard factored form games, SFF games. Example 4. Let's find the standard factored form of n equals 750. Find the standard factored form of n equals 750. Okay. All right, so there are a lot of ways to do this, but I like to just go in order because I know I'm going to want these prime factors in order anyway. So I start with the smallest prime that I think might be a prime factor of n. So the smallest prime is 2. We all know that. So the first thing I do is I look for copies of 2. And I ask, does 2 divide n? And yeah, it does, right? Because n has its last digit in the ones place is an even number, 0, 2, 4, 6, or 8, we know that n is even, and there's going to be a factor of 2. So we can pull out 2, and of course that leaves 375 behind. So like I said, I just try to be methodical. You can use a calculator, it's fine. All right, now, I'm looking at 375 because that's what I'm going to try to break down next. It's not an even number, right? So I know that 2 is not going to divide into 375. So we're done with 2's. There's no more 2's as factors of n. There's only 1, 2, okay? Now I want to show you this trick about 3. So like I said, I'm just going to go in ascending order. The next prime is 3. Do you know the trick about how to know whether or not a number is divisible by 3? Does anybody know that trick? No? No, you didn't learn that one in high school? Okay, so here's the trick. What you do is you add up the digits of the number. 3 plus 7 plus 5 is 15. If the sum of those digits is divisible by 3, and 15 is divisible by 3, then the entire number is divisible by 3. It's a really nice, quick way to see if 3 divides the number. And it works for 9 as well. If the sum of the digits is divisible by 9, then the number would be divisible by 9. So this is definitely divisible by 3. So I know I can factor out a 3, and in fact, what's left is 125. So now we want to break down 125. I want to check and see if there's a factor of 3 in 125. So 1 plus 2 plus 5 is 8. 8 is not divisible by 3, so we're done with the 3's. There's not another factor of 3 in n, right? So what's the next prime after 3? We're going to try to do them in order by size.
5.
Yep. Does 5 divide into 125? Of
Yes.
course, sure. So we've got 2, times 3 times 5 times 25. And of course, we all know that 25 is 5 squared. So all of a sudden, we can see that 750 is 2 times 3 times 5 cubed. This is the standard factored form of 750. We've got these primes written in order, right? And like, this is prime 1, this is prime 2, 5 is prime number 3. There's 3 primes. K tells us how many different prime factors there are. All right, this K tells us how many different prime factors there are, okay? We have 3 different prime factors. And so go ahead and find, just to practice, to make sure you're comfortable with this notation, find each based on equation star from the unique factorization theorem. We'll see what I'm asking for here in just a second. All right. 1, find K. Okay, so we're looking at the unique factorization theorem. I'm going to pull this up. So I knew that would happen. Hang on. Okay. I just want you to be able to see that. So find K, find P sub 1, find P sub 2, find, oh no, wait. Before you find P sub 2, find E sub 1. Then find P sub 2, and then find E sub 2, and find P sub 3, and then you can find E sub 3. So what is K, folks?
Three.
Yeah, K is 3 because we have 1, 2, 3 different primes, right? P1, P2, P3. So K is 3. What is P sub 1? Prime 1.
Two.
Yep. What is E1? What's the exponent that's on prime 1?
One.
Yep, good. 1. Excellent. What's P2?
3.
Yep. Right, the second prime is 3. What is E2, the exponent on P2?
One.
Yay, everybody's seeing it. Great. What's P3?
Five.
Of course. And then E3, of course, is 3. So, I mean, when we see an example, it makes this a lot less mysterious, right? So let me give you a do later. And there's one of these on special homework 6, of course. But if you feel like you want a little more practice, you can always bring this into um, office hours, if you want some help. Find the standard factored form of n equals 1260. Okay. So we have a little time left, and I would like to talk to you now a little bit more about perfect squares and perfect cubes. I know you've already got experience with perfect squares. I'm going to try to risk pulling the camera down. There we go. Make it a little bigger for you. Perfect squares and perfect cubes. There's some interesting stuff that happens when we look at the standard factored form of perfect squares and perfect cubes. So here's a fact, and we're going to verify this fact. If x greater than or equal to 4 is a perfect square, then every exponent in the standard factored form of x is divisible by 2. Now, why would that be? All right, well, let's look at it. The answer is basically because if x greater than or equal to 4 is a perfect square, then by definition of perfect square, x is equal to n squared for an integer n greater than or equal to 2, right? And we are going to look at the standard factored form of n and then x. That's our game plan. So we're going to look at the standard factored form of n and then see what happens to x. Let's look at let's just keep the claim, this fact up where we can see it. This fact says if x greater than or equal to 4 is a perfect square, then every exponent in the standard factored form of x is divisible by 2. Okay, that's what we're going to try to show. That each one of those e sub i's is actually an even number. All right, so first let's look at the standard factored form of n. N is at least as big as 2, so it's got 1. So n is equal to p1 to the e1 times p sub 2 to the e sub 2 times dot 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 times p sub k to the e sub k. I'm not going to write all the other stuff. We know that the p's are prime and that the exponents are positive integers, okay, and that the primes are written in ascending order by size. None of that actually matters that much until the end. All right, now let's look at x. X is n squared, right? So we take this whole expression for n and we square it. So p sub 1 to the e1 times p sub 2 to the e2 times dot 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 times p sub k to the e sub k. That whole thing is getting squared. And now remember rules of exponents. If x is being raised, so if x is being raised to the m, so x to the m, if that quantity is getting raised to the n, what do we do with those exponents? Does anybody remember?
You multiply them.
Yeah, we multiply them. Good. So let's just review for folks that don't remember laws of exponents. So we're going to use that, but before we use that, we're going to use the fact that x, y raised to the k is x to the k, y to the k. The fact that this exponent 2 can get distributed across these factors. We already used this earlier, right? We're just using it in the other direction. So it's p sub 1 raised to the e sub 1 squared times p sub 2 raised to the e sub 2 getting squared. This 2 is coming across and multiplying times each of these factors times p sub k to the e sub k squared. And now we use the fact that when we raise an exponent to an exponent, we multiply them together. And when we multiply a variable times a number, we usually put the number first. So that's p sub 1 raised to the 2e1 times p sub 2 raised to the 2e2. See it? Times dot 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 times p sub k raised to the 2e sub k. So notice every exponent, right? We were trying to show every exponent is divisible by 2. We'll check them all out. They've all got a factor of 2. Notice every exponent has the form 2e sub I, where, of course, the e sub I is a positive integer, so it's an integer. So that means 2 divides each one of these. Any questions? So this is just a direct result of laws of exponents and the fact that we're looking at a perfect square. But what if we were looking at a perfect cube? You can do this one later. Look at the standard factored form of x equal n cubed, a perfect cube. And in order to ensure that n is at least as big as 2, so to ensure that n actually has a standard factored form, we're going to require that x is at least as big as 8. What can you say about every exponent? in the standard factored form of x equals n cubed. What do you think you're going to be able to say?
X is divisible by 3.
Yeah, each of these exponents is going to have a 3, right? Because it's going to be n cubed. So this 2 is going to be a 3 that's going to get distributed. And each of these exponents is going to look like 3 times an integer, right? And you can play this game ad infinitum. You know, if x is a perfect quartic, you know, it's equal to n to the 4th, then every exponent in the standard factored form of x would have a factor of 4 in it, and so on and so forth. So I am going to drop a very short video over the weekend because there'll be one problem that we haven't done anything quite like it. But there are some nice WebAssign problems that you'll be looking at. 4.3 and 4.4 have already been posted, you know, for several days. Go ahead and work on those. And there is an interesting problem about perfect cubes that, you know, having to do with the standard factored form in the WebAssign. So there's one problem in special homework number 6 that's going to have to do with standard factored form of numbers in general, cubes and squares in particular. So I'll post that tonight or first thing in the morning for you to work on. Any questions? All right, so we're not quite as far along as I wanted. I'm going to have to get into the reading page and adjust a little bit. We're just a tiny bit behind, but you know what? I can live with it. If you can live with it, I can live with it. I think that this material takes a little while to soak in. I didn't want to just fly through, you know, this material from chapter 4 because, you know, it gets kind of deep. So we'll start 4.5 on Monday, and that is going to be where we learn proof by cases and the quotient remainder theorem. So that's something to look forward to. We have an office hour here at 8 p.m. So if you have any lingering questions about anything, you can come in, or if you want to look at some of these due later problems that have been introduced tonight in lecture or in Monday's lecture, please feel free to come into the office hour. All right. Thanks for playing. I'm going to stop recording.